Hello, and welcome to another day of daily LeetCode streams where we just do LeetCode for fun and hopefully learn a thing or two while doing it. So if you're new to the channel, if you like doing LeetCode, if you want to see someone do LeetCode live and learn things along the way, and maybe you're also on your own journey, be sure to subscribe to the channel. I do this every single day at 6 p.m. Eastern Time, and on the weekends, I normally do it whenever I wake up. If you really want to be kept up to date and you want to have the best of both worlds, also ring that notification bell. It really helps me out, and it helps me expand my reach out further. So, just a quick couple of things. Yesterday, I went ahead and I made another update to my website where I have this sort of curated list of questions that we've come across that I believe to be top quality questions for someone looking for a different way of approaching LeetCode. Some of the things I did was I added this bar up here that now just reflects the amount of questions I have on the list so far. You'll see that we're currently sitting at 0 medium and 0 hard because we just haven't gotten to those questions yet. But when we do, those will start showing up here. Also added a link to the Discord that I've created a couple months back. If you're also looking to be able to discuss with a real-time community, be sure to join the Discord. We're sitting at around 1,300, maybe 1,350 users, so really proud about that. That community is very active and it's constantly growing. We have a great set of users over there. All right, so just pretty much continuing where we left off. Let's see if we can get over that 150 mark. We're sitting at 147 questions right now. Let's go ahead and try it out. So I'm going to click on algorithms. I'll go to easy, sort by acceptance, excuse me, and we'll go ahead and go to page 2 because that's where we are. All right, let's start off with a really nice one here. So this is the average of the levels in a binary tree. So they want us to get all the averages, right? So this is 3, this is 9 by 20, right? So that's 29 divided by 2. On level 1, it's 14.5, and on level 2, it's 11 because 15 plus 7 is 22. So one thing that I like to do here, this is a breadth first search traversal, right? How is it that we can sort of iterate through every single child on each level and come up with an average for all that, right? That's exactly what we're going to do. But it's not so much of, how do I explain this? Like we can't really do, I mean, I guess we could do sort of like this way, calculate these children, calculate these children, and you can come up with something based on that. But we can just do a standard level by level traversal, and I'll sort of walk you through how I do that. This is frankly just an algorithm that I memorized, but we'll go ahead and look at it here. So let's imagine, let me draw this out because I think this is a good opportunity to draw it out. So we have, if we come here, 3, 9, 20, 15, and 7. So let's just go and start drawing our nodes. 3, 9, 20, 15, and 7. Come over here, right there. Was it 3, 9, 20, 15, and what was the other one? Was it? Oh, this is a binary tree. It doesn't even need to be. Okay, 15 and 7. Okay, sweet. So if you think about it, what is it that we want to do? Let's start creating an array and seeing how that sort of like helps us out here. So imagine that we start off with 3, right? Because 3 is the first thing in this root, right? Now 3 is on a level of its own. So one thing that I learned a while ago is there's sort of a way that we can keep track of the level we're on, or we can sort of know that we haven't reached a new level. So we can use something that's called like a sentinel value. A sentinel value is something that you might come across in other questions like linked lists, especially, where you might create this sort of like sentinel node that acts as a temporary pointer to the head. And at the end, you just return its next pointer, which is the actual head of the list you want. So imagine here we have 3 and null. Let's say we keep track of some sum, right? We say, okay, our sum currently right now is 3. And then whenever we reach null, then we know we're about to come up to a new level, so we have to sort of calculate the average, right? So we calculate the average from here. That will give us 3 because 3 divided by 1 is 3. So I'm going to add that to this one here. And also these will be popped, right? Because we're going to consider 3. We're going to push its children, right? So that will be 9 and 20. And then we're going to DQ3. And then the next time we DQ null, then we go ahead and do that calculation I just told you about. So now we have null out. Now we do 9. We look at its children. It doesn't have any children, so we don't do anything. And then we look at 20. It has 2 children, so we push them, we queue them onto our sort of queue here. Now, something I forgot to mention is anytime we do come across a null value, at the same time that we pop that null value, we also have to push it. So let me just make sure we have everything right here, right? So we DQ3, we push 9 and 20 because it does have children, 9 and 20. We see null, so we DQ null, and at the same time we add null over here, right? We DQ 9, it has no children. We DQ 20, it has 2 children, which is 15 and 7. And now we're gonna DQ null. We'll push the null here. And now next time we come right back around to our null, we can also check, well, if it's null and the array is empty, then we know we have no other nodes to process. So that's gonna be sort of how we discover how many, discover the average, right, for each one of these. Now, something I just noticed is the average will always be, and let me just make sure, right? So it's 3 null. By the time we reach a null, how many elements have we processed so far? I guess anytime we process a new element, as long as it's not null, we can increment some counter that represents the amount of elements on that level. That's something that I'm thinking of doing. So let's start writing this out and see what it looks like. So we know we're going to start off with what? We're going to start off with, and I guess, are we ever going to have an empty null, an empty node? Okay, we're always going to have at least 1. So here we can create const, and let's just call this q. Let's make it equal to root and null. Here we can say, well, q.length is greater than 0. What is it that we want to do? So here we're going to say const node is equal to q.shift. I believe shift is going to move everything to the left. And just to make sure, it will get me the first thing, right? MDN shift removes the first element from an array. Okay. Oh, okay, clicking in a ton of different places here. So what is it that we have to check here, right? We have to say if node is equal to null, we'll go ahead and do something. Else, if it's not, what can we do? We can say if node.left not equal to null, we can say q.push node.left. If node.right not equal to null, we can say q.push node.right, right? Now, there's a couple of other things we have to do here. Like anytime we get a number, so imagine we're sitting at that 3 and that null. So I'll go ahead and draw that here, just like what we had earlier, right? This is the first thing we start off with. Let's go ahead and create, let's say node count equals 0. This is going to be the amount of nodes on a specific level. And we can also say total equals 0. Or perhaps sum. I think that would be a better thing, right? And let's also make another variable here that we'll use to keep track of our results. So we have const result. So what needs to happen? The first time we shift this, right, we pop 3 off, right? If it's not null, that means we can add node count plus or equals 1 and sum plus or equals node dot val. I think it's val. Yeah, val right here, right? And then we can go ahead and worry about adding the children. Now the next time, well, actually we'll add the children first, so we get 9 and 20, right? 9 and 20. Then we come back to the top. Q is greater than 0, so we DQ null. And now it says what? If node is null, which it is, remember that we can check if q.length is equal to 0, then we can just return our result here. Else, to the result, we want to add result.push the current sum, and we'll do a math.floor. We want to do the current sum divided by the node count. That'll give us our average, right? We also want to push a null to signify the next level. We want to reset node count to 0, and we want to reset sum to 0. And this really should be the algorithm here. Again, in the bottom here, I'll also return result, although I suspect this one should always return. At some point, it's going to be empty. But let's go ahead and run this. Okay, so there's a couple things that we missed here. We missed this last one here. Okay, so let's check this last one. I think what we need to do is before I ever before I ever check for that last one, I need to also push this, right? And now, what does it want me to do? It said 14.5. So are these always guaranteed to be nice looking numbers? Do I not have to, does it not care that I'm truncating it? 14.5 and 11, 3, 3. Okay, that looks good. Ran it too quickly. How do you know you're going through every node? I'm not sure what you mean by that. How do I know that I'm going through every node? 97.67. Do you mean like based on, do you mean because of the nulls that I'm writing? Sorry, my first time doing a tree problem. Oh yeah, no, it's no worries. I just wanted to, I was asking because I wanted to make sure I understood the question. That way I can help, like, I can better answer it for you. So let me go back to my drawing here because this is pretty nice here. So in tree problems, especially this one that requires us to do like a level by level traversal. So if you think about it, we're going to process everything on this level, we're going to process everything on this level, and then we're going to process everything on this level. It's a different type of traversal where we're not doing like an in order, a pre-order, or a post-order. This is a level order traversal. And the way that we do that is by using breadth first search. So let me show you how this works. The first thing we do is we initialize an array that just contains the root, and we immediately also put null. What null helps us decide, null here is something that we call like a sentinel value, or like a special value that allows for me to know when I'm about to get to the next level. And I know that since this is the only thing on the first level, I can immediately put null. So now let's see what happens as I start processing this array, right? I go here and I say, let me DQ3. That's the first thing I want to process. Okay. Now I check to see, does 3 have any children? Okay, 9 and 20, it does. So I'm going to add 9 and 20 to the queue because at some point I want to get to that, right? And I can do whatever other processing I want with 3. Like whatever you want to do, and when I say whatever you want to do, it's really dependent on the question. Here we want to figure out the average. So because the first time I shifted the node, it was not null, it was 3. I don't get to this if, I just do my else. This is normally where your logic is at. In this case, we're keeping track of this average. So, you know, I'm incrementing the amount of nodes I have, and I'm also adding to my sum. So at the end, when my node is null, I can process my sum and node count, and that's how I get my average. If I keep going through this, all right, we just DQ'd 3. We got the average, and we put it inside our result here. Now, when we go and DQ null, right? When we DQ null, we do our processing, and actually that's when we would include the 3 here, and we reset our sum and we reset our node count. Now, anytime I see a null, I also want to immediately push a null to the end, because that means that I've already reached the end of like the level that I was on, right? Because the null signifies that. The null signifies that I've already reached the end of the level, so push another one onto my array. That way the next time I get to one, I already know I'm at the end. So let's DQ the 9, right? There's no children for 9, so I immediately DQ the 20. I see a 15 and a 7 here, so I can push 15 and 7, right? Now I DQ my null. I do whatever processing I want with 9 and 20, which I think the average was what, 14.5. Then I reset my sum, reset node count, and again, I push null. Now we start this over again. I DQ 15, right? I DQ 7, then I DQ null. Now here, if you look at it, this is the first time that we have an empty array. So it's kind of like a special case, and it just so happens that we have no other nodes to process. So we know that first, let's go ahead and output our average, which I forget what it was, so I'll just put 10 here, for example. Or 15 and 7 is 22, so what, it should be 11. And then we say, okay, I push my average, and now the array is empty. So that's sort of a special case. We haven't seen that before, and it does coincide with the fact that we have no more nodes to process. We know we're done. We've processed all the nodes. So I hope that explanation was helpful. And if you think about this, like this array here, like the time complexity here is going to be O of n, right? Because we need to go through every single node inside of this tree. And now the space complexity, if you think about it, I think it's going to be bound by, right? If I go 3, right? So I take off 3, I add 9 and 20. I take off the null. No children for 9. Even if 9 had children, it's always going to be bounded by the largest level. Or actually, is it even the largest level? Because even if here even if 9 had children, let's say 9 had children like 7 and 9, right? And then 20 has children, 15 and 7. If 7 had children, I'm kind of just messing with something here, 15 and 6. I'm putting arbitrary numbers, so don't be like alarmed. I'm just seeing how large this would grow. I think that this would just grow to be as long as the last level, however many nodes are in the last level. So I guess we can say it's bounded by the length of the longest level or the widest level in the tree. I think that's something that we can say. It kind of makes sense to me, because a lot of times we also say that in like a post-order traversal. It's like here we're going left to right on every level, right? If we're doing another traversal like pre-order or post-order, normally we say if a tree is height balanced, for example, this tree is height balanced, it doesn't differ by more than one node on any given node, then we say the space complexity for that is just bound by the height. So I guess when we do a level order traversal, we can say that the space complexity is bound by the widest level in the array. So yeah, we end up with this nice algorithm, extremely important to learn. Can't really emphasize this enough. I highly recommend to practice this. I mean, this is something, like I said, I kind of memorized this. I can bust this out fairly quickly. I would also encourage you to do the same. Cool. Let's get to our next one. Univalued binary tree. This one used to just like really trip me up, but I finally understand it. So let's go ahead and work on it. So we have nodes on every level except for the right one on the left. Okay, so I'm going to do that. 1, 2, 3, 4, 5, 6. So let me just remove all this. We're going to start our whole thing again here. Draw our circle. 1, 2, 3, 4, 5, 6. All right. Univalued binary tree. So what we want to find out is, does every single node in this tree have the same value? Now, you might think like in recursion, right? I mean, I look at a tree and I automatically think about recursion. So you can say, well, it has the same value if every tree to my left and every tree to my right has the same value as me, then I know it's univalued. And similarly in this one, if I say if every value to the left and every value to the right is similar, then I know we're good. So let's think about sort of like the base cases, right? Imagine we just had like, I guess we can think about this in a couple different ways. And it's actually good that I haven't done this problem in a while. Imagine we had just like a null node, or we have a leaf node, or we have a node with a single child, or we have a node with multiple children, right? So let me just like move this. These are like the different edge cases here. Not edge cases, but sort of like cases I want to consider. I'm going to move this guy over here. I'm going to move this over here so we can like write on it. So I think that if we have a null node, then we should just return true, because I feel like a null node should mean that it's univalued. And I think similarly with, I think return true for a leaf node, right? Now for node with a single child, we just want to make sure that whichever one has the node, as long as it's the same value, so whichever has the node and same value, return true. And I guess we can say the same with this one, like as long as both of them have the same value, then it's good. So let's see how we can start writing this, right? Like, what's one thing that we can do? I kind of want to go in like a post order fashion where I look at all my children first, and then at each parent, I make a decision. So let's remind ourselves of our base case, right? We have if root is equal to null, or let's see, if roots is equal to null, or root dot left is equal to null, and root dot right is equal to null. And let me just make this a little bit clearer. Here we can return true. So in either case, now we have a situation where, let's see, is univalued. Yeah, I think now we can just check to see. So let's see, at every place, maybe we can do the left and the right equal to myself. So left equal. So how do we know if it's left equal, right? If we have, imagine we're at this one right here and the left is null. If the left is null, then it automatically is equal. There's like nothing, we can't really do anything there. So I think we should say const left equal. We can say, I'm trying to think, I'm trying to be clever here, but I don't think I should. We can say like if root.left is equal to null, then we just return true. Else we can return root.val equals root.left.val. That's for left equal. And then for right equal, it should be the same thing, right? So right equal, if root.right is equal to null, then it's true. Else we just check if root.val is equal to root.right.val. And now we should be able to do return. Let's say we want to do return left equal and right equal and is unival tree root dot left and is unival tree root dot right. Let me run this and see what we get. True and true. For this next one, true false, true false. Let's run it. Okay, so I hope the image, I hope this image was helpful, right? But I think these are like some nice base cases to consider when doing anything with a tree. Like what happens if we have a null node? What happens if we have a leaf node? What happens if we have a node with a single child, or we have a node with multiple children? And I'm saying multiple and not two, because it doesn't necessarily need to be a binary tree. It could perhaps be an n-ary tree, right? And that might change things a bit. So it can be multiple children. Now, yeah, that's a very, very important skill. And that's something that like me drawing this helps me out. I also hope it helps the viewers out. But I think it's very important to take the time to draw pictures out, and because like you'll often see things that you can't if you just try to do it in your head. And I realize that sometimes you're just sitting up in front of your computer and you're thinking like, no, I can do it. Like I can just figure it out in my head. But I promise you, if you just take a little more time to draw it out, it's gonna be really great. So to explain this part right here, the reason for the single child is because we don't, it's almost like what we set up here, right? Return true if it's null. Like if we only have a single child and the child that we're checking is null, we don't need to do anything. It's just automatically true. There is nothing to check because it's null. That's like one thing I want to make clear here and why I sort of went in this direction. Now, could we make this nicer? Like if I just do, if root null, it's going to return true. This returns true. Root.left equals null. Let's see if root.left equals. Yeah, I think this might be like, I'm okay with writing it this way. And I like the solution that we got, 77.56. Again, for this one, this isn't a binary tree, right? And there's not, or rather, this is not a binary search tree. So we have to visit every single node. It's going to be an O of n, a linear time algorithm. As far as space complexity, the same thing I said before. This tree is height balanced, right? This is actually, it's not a complete tree, but it's a height balanced tree. So this would just, the internal stack will only ever grow as large to be as the tallest, or the tallest path. right? So it's bound by the height of the tree. This one's also height balanced. Let's run this one more time. 96.59, yeah, pretty happy about that. All right, Fibonacci number. That's exactly what I made today's stream about. I think this one's really cool. And again, we're gonna do a drawing because this really, really helps here. We're gonna remove all this and we're gonna do Fibonacci. So f of 0 is 0 and f of 1 is 1. So f of n 1 and 2. Okay, let's take an arbitrary number. Let's take 4. I think 4 will be good. And we're literally gonna do this ourselves. So anytime we do Fibonacci, right? You can think of this as sort of being, this is recursive in nature, right? Because we're calling another function with f of n minus 1 and another function with f of n minus 2. Let me also go back and make sure that I like this question because I really do like this question. Univalued tree. Right, so let's come back here. So we have 4, and let's remind ourselves of the function here. So f of n minus 1 plus f of n minus 2. Okay, so let's imagine we call, we're going to start here in the 4, we're going to call f of n. So we're going to slowly build out our tree. So I'm going to copy this, we're going to move it here. This is going to be a 3, right? Because that's what we're calling it with. Cool. Now we call this one again, right? Because we're doing f of n minus 1. This time we're going to call it with a 2. Cool. And what I should do, I should make this smaller. I think some of them are going to be a little bit lopsided, but just bear with me. That way I can fit this all into the screen. Okay, 2. Now we're going to call it again with f of n minus 1, which is 1. But here at 1, we're done here, right? Because we know that, what are the cases that we have? F of 1 is 1, right? So as soon as we get to one of these base cases, which is 1, we can break. Now we come back to the 2 and we do f of n minus 2. So now on the right, we get here. We call this with 0, right? Same thing, that's a base case. So we break out. Now we come back to this one. We call this one with a 1. That's another base case. So we break out of that. And now here is the important part. We're going to call this right one with a 2, right? But look at this. This is the big takeaway. I'm putting this one all the way out here. You can absolutely solve the question this way. And let me see if I can copy all these. That would be really nice. Is it going to let me? I want to copy everything but that arrow. I guess we'll take the arrow. Remove this, remove this. You notice anything here? Check this out. So this trio of nodes, we've already solved it previously, right? It would be nice if we can take advantage of the fact that we've already calculated this, and as soon as we see a 2, don't even bother looking in the left and the right. That's exactly what memoization is. It's a type of, I think it's a type, and I say I think because really I've forgotten, but I think it's like a variation of dynamic programming. You might hear top down or bottom up. I think dynamic and memoization are just those variants, the names for those variants. So we're going to essentially cache the results to be able to figure out the answer. But before we do that, let's do it exactly how they're telling us here, right? So if n is equal to 0, we return 0. If n is equal to 1, we return 1. Else we just return fib of n minus 1 plus fib of n minus 2. And this alone here should give us the answer. 1, 1. 1, 2, 3, 1, 2, 3. Let's submit this. Okay, 26.57. Now, probably being able to solve this question, I think, is a cool milestone. And you did it recursively, and we should probably talk about the space and time complexity. stored in a function call during recursion. It's like kind of like that, right? We can pass in a parameter that allows for us to keep track of a cache. That's at least how I've seen it in JavaScript. I'm sure there's a ton of other ways of doing it. This is at least how I've seen it. So I'll kind of go through it that way, and hopefully that translates easily into your language. Something that I try and tell people, or like advice, is learn concepts, not syntax. Because even though you might see me doing it in JavaScript in one way, like you should be able to grasp the concept and be like, okay, I know how to do that in Java or C# or C++, so I just got to translate that into whatever syntax is appropriate. So let's think about what happens here, like at every step, right? At every level, we've essentially like doubled our case, right? Because here we have level 1, right? At level 1, we just have one node. At this area, now we have 2. Here we have 4, and you can imagine at the bottom here we'll have 8, right? And that's if we decide to go in this way. So it means really like this is a 2 to the power of n algorithm, where n is just the I guess, what does it actually come out to? Yeah, I guess n. Yeah, 2 to the power of n. 2 times 2 is 2. Is that going to equal 16? We have 8 in the bottom plus 4. That's 12, 14, 15. Oh, maybe it's 2 to the power of n minus 1. Maybe that's like the time complexity. That's how many nodes we end up with and how many nodes we actually have to traverse. Because at every single n, we're like doubling the amount of nodes that we have. So that's what the time complexity for this ends up being. Yo, what's up, MMD? Good to see you again. That's what we end up with here in time complexity. And space complexity, I believe, is just constant because there's no extra space. I mean, internal stack space, but I suppose that for this, it would also be height balanced, since like, well, at least in this case, it's still a height balanced tree because we never have more than one of a height difference between any nodes. That's what I would say. That's sort of like my analysis for this. Okay. That's a cool drop. I like too. Nice. Thanks a lot. You guys have been like troopers. Like you guys are the OG original people that come on all the time. There used to be this other guy called Rashawn. Haven't seen him in a while, but it's really cool to see you all here. I've definitely been trying to like expand my reach and trying to get people, trying to get more people to join in, because I think it'd be even more fun when we get a lot of people on the chat and everyone's talking about LeetCode and just like different ways of doing things. But we will get there. Stick around. I'm not stopping anytime soon. We have so much work to do, so we have a lot more to achieve as we do this. Okay, sweet. So we figured out this way. Let's now think about this memoization solution, right? So pretty much what we want to do is like, we'll calculate a result first, and then once we're done calculating that, it's just like a cache, right? Like we can check the cache first. If the cache for number 2 exists, we just return that, else we'll just solve for that. So really what we can do, let's think about this. What will be a nice way? I think here, so I want to make it that if n is 0 or n is 1, that's a base case, so we have to do that. So really what we can do here is, what if we had an object called memo? It was an empty object, and we can check, right? We should check the cache first. If like memo of n is not equal to undefined, that means there's something in there. For that n value, we can just return memo of n. Else we want to set memo of n equal to this expression, right? Memo of n equals this, and then at the end we just return memo of n. And I think we can leave these returns up here. Let me just check this. One, two, three, 1, 2, 3. 5%? No way. There's no way that this is slower than the previous one. Oh, wait. I know. We're not actually... We need to take advantage of our cache, no? Okay, there you go. That's what I want to see. Those are the numbers that I want to see. So now calculating the time complexity for this, to me, let's see. I guess we're only ever going to go 4, 3, 2, 1, 0. So would it just be linear? Because now we're only ever calculating it for the time that we take, right? Because we do 4, 3, 2, 1. We calculate all these. And the 1 and 0 are both constant, right? Because that just is a single return. And then by the time we get to 2, that's just constant because we're returning it. So I think it's linear because we only process all the nodes from n to, I guess, 2, from n to 2. Let's see what the discussions say. Java solutions. Okay, cool. Yeah, time complexity. And is this using... Whoa. Oh, iterative. Okay, I see. Okay, 2 of n, right? Space complexity, recursive, top-down approach. The space. Oh, and then space complexity for the O of n. Okay, sweet. Bottom-up approach. Return fib of cache. Okay, so I think, okay, this is what I was telling you guys earlier. So I guess a top-down approach means memoization. Now, does memoization necessarily mean a cache? Perhaps. Memoization, I guess memoized means to return some cache. Here, the bottom-up approach with dynamic programming, well, we're still creating a cache here, but now we're creating an array. Why would that be bottom-up? We're creating an array, and then we're using those values. Maybe with top-down, we're building the object on the fly and then using the values. It's an exponential time. At every single frame, we're calling 2 other functions, so that grows exponentially. So yeah, everything checks out with what we analyze and what we talked about. So I'm very happy about that. How do you guys feel about it? This one's a very important question. Like it's a pinnacle of LeetCoding to be able to know how to do this question and understand it. I definitely think like I really hope that these drawings help. I would encourage you all to do the same, like on a sheet of paper, on a napkin, on your whiteboard, whatever you want. Just like draw this out and understand why the memoization works. And what I'm really excited about personally is I've practiced this problem before. I'm not talking about before like this stream, even longer. Like a year ago, I learned about this. The true moment for me will come when I can apply this same technique to like a medium style question or one that I've never seen before. Because as I continue doing more of these LeetCode questions, we're going to start to get to some that I've really never ever worked on before. The concepts are interesting and I like the different approaches. That's awesome. That's super cool to hear. And I think we're doing great on time. We've done 3 questions. We got like about 20 minutes left, so I'm really happy about that. So let's keep going. Whoa, I hate when that happens. Let me remove some of these things. Let me just check on the stream real quick. All right, everything's good. All right. Which one did we have? Average, nope. Greatest English letter in upper and lowercase. All right, given a string of English letters S, return the greatest English letter which occurs as both a lowercase and uppercase letter in S. The return letter should be in uppercase. If no such letter exists, return an empty array. So an English letter B is greater than another letter A if B appears after as both lowercase and uppercase. Okay. Given a string of English letters, return the greatest English letter which occurs as both lowercase and uppercase. It's greater than another letter A if B appears after A. Okay. R is greater than F or A. Because R, Letter R is the greatest letter to appear in both lower and uppercase. Note that A and F also appear in both lower and uppercase, but R is greater than F or A. Oh, I see. Okay. It's literally just Sorry, I heard something weird outside. That was weird. Okay, I see. It's literally just like the Unicode value. So what do we want to do? We're going to need to keep track of, there could potentially be multiple greatest characters. And I guess at the end, once we have this array, ooh, I'm almost thinking about using, I think I know what we can use here. So this is something I've learned from here. Like, if this is just ASCII characters, consists of lowercase and uppercase English letters, if this is just ASCII, right? Let's think about the ASCII table. Very important to know over here. I mean, you don't have to memorize the table. You just have to know that this like encoding exists. This goes up to 127, right? We can represent all uppercase and all lowercase letters in this array. So I think we can create a statically sized array of size 127 or 128, right? So we can actually index 127, and we start adding the frequencies there. And really, we just want to find the first one. I think that's, let me think about this. We want to find the first one that appears twice starting from the end, right? Like if let's say they said R was the best one. The letter R is the greatest letter to appear in both lower and uppercase. So imagine we're coming from the back here, right? We start going like looking through all these characters, and we get to index 114, which is R. Like this would, if there was another one that appeared, then I know its uppercase equivalent would have also appeared at least once. So that means it appears twice, and it's the greatest one. So since we started from the back, right? It necessarily has to be the largest one. So I think that's what I want to do here. I'm going to say const ASCII is equal to a new array. I'm going to fill this up with 128. I'm going to fill this with 0. Now we're going to go through each one of the different characters. And I think what we can even do, oh, it'd be nice. Yeah, I can actually do something. I can do a twofer here. If I want to map through this, do we even need to? No, I gotta take the frequency. I can just leave this like this. I can just leave that like that. Let's do for const C of S. So I'm using C to stand for char, like character. We can get the code c.char code at 0. Now, normally I normalize this, right? I do like minus 97 because I want my lowercase a to be mapped to 0. But this time we have an ASCII array. We don't need to do this. So all we need to do is say ASCII of code plus or equals 1. And now what I can do is say for let I equals ASCII dot length minus 1, I greater than or equal to 0, I minus minus. We want to find, like, so if I get to a spot where ASCII of I is greater than 0, so that's a contender, right? Now I need to find its equivalent uppercase letter. I think it's just like to get from what, 114 to 82. 114 minus 82 is 32. So I think we can just do, let me just write 32 here to remember. If ASCII of I is greater than 0 and ASCII, now do I always want to do, I should probably also check to see, let's do a couple of things here. If ASCII of I is greater than 0, yeah, because I need to do a bounds check here. If ASCII of I is greater than 0, let's make sure that I is at least, if I is greater than or equal to 32, and ASCII of I is greater than 0, and ASCII of I minus 32 is greater than 0. So what does this mean? Why am I doing I greater than or equal to 32? In this case, we didn't have any double letters. So if I make it all the way to like I equals 5 and I try to do 5 minus 32, I'm going to get an index out of bounds. So I need to make sure that I'm only doing this calculation for values that are greater or equal to 32, right? Because that's the differential here. Then I'm saying if I'm currently at a lowercase letter, if ASCII of I is greater than 0, right? Because lowercase letters are the first ones that I'm going to find in this table, right? And ASCII of I minus 32, this is to find its corresponding uppercase letter. If that one's also greater than 0, then that means these have appeared more than once, which I think is all we care about, right? Both as lowercase and uppercase letter. We can just return, they want us to return the uppercase one. Okay, now we can just actually return. There's another really cool function here called return string from car code, I think is the thing. Let me see, from car code. Yeah. From car code just takes that decimal value and creates a string. So here we can just do I minus 32. Else we just return an empty string. That's what they want, I guess, right? Yeah, let's see if this works. That's E and E. First test case worked. So ER empty string, ER empty string. 96.71. Yeah. This was a very cool question. This, yeah, high quality question. That's very cool. A couple things that we did here, right? So this, like, if you've read Cracking the Coding Interview, I think the first section is all about strings, and the first question is very similar to like figuring out the frequency of different characters in a string. Gail, the author, literally says, like, she literally recommends this optimization. Like, ask your interviewer if you're only dealing with characters from the ASCII set, because then you can optimize doing something like this. Or maybe if you also have to deal with Unicode. Like, it's good to know these different formats, and then you can optimize by creating these data structures. That's why we were able to create this array, because I know that we're only going to be doing lowercase and uppercase, so I can just include characters in ASCII, in the ASCII format. And then what I do is I go through each one of the different characters in S, I get the code, and then I just increment the frequency there. Now what do we do in the bottom here? Here we're saying that we're gonna go through the entire of ASCII, right? I'm gonna start from the back, and I guess let me think about this. I could have, oh, because it wants the one that's the greatest. That's the thing. We need to find, there can be multiple that have, like, right, like they said, R, A, and F, but because R is the one that comes later. So if we start from the back, then the algorithm already handles that for us. The first one that we find that satisfies the condition will necessarily be the greatest one. So we do that. We do this out of bounds check to make sure that we're never checking this if we're like over. And I guess really, like, do I even want to do, let me see, ASCII greater than or equal to 32? Perhaps I can just do this, right? It's greater than or equal to 32, and then I can just check for those two things. I don't even need to do that other check there. I minus minus. All right. Let's just submit this. 90.60. All right, it's pretty cool. Yeah, so that was a nice little optimization we made there. Let's think about time complexity. Like, to make this array right here, right? It's just, it takes, well, it's always going to be constant. The array is always going to be size 128, so it's not like variable. It's not dependent on the length of S. It's just always going to be this. For const C of S, right, this will be bound by the size of S. So this will be O of N, where N is the length of S. And then this array, since we're looping through ASCII, which we know is constant, this loop will always be constant. We're always going to go to the end, and we're always going to go from the end, and always going to go until I is greater than or equal to 32. That's constant time complexity. So really, we're bound by this for loop here for a linear algorithm. And then as far as space complexity goes, we also have constant space because we're just creating this single array of size 128, and then everything else is just constant. So constant space, linear runtime. In Python, there are built-in string constants that simplifies this a lot. Cool question nonetheless, and cool to see it in a different language. Yeah, Python, I've seen some crazy stuff, like, which I think it works in both ways. Like, you definitely don't want to, I think the best thing you can do in an interview is Well, let's talk about the worst thing. The worst thing is just using, like, imagine JavaScript had like a greatest letter function for whatever reason, and in my interview I just do something like return s dot greatest letter, and I'm like smiling and saying, oh my god, that's so great. I think the best thing to do is you do this thing first, and then you mention to the interview, you say, hey, so for example, in JavaScript, like one of the newer iterations of the JavaScript language, a very popular iteration of it is called ES6. There's other versions now like ES 2020, and I'm sure ES 2021, 2022. But ES6 introduced a lot to the language. So something that I might say is, oh, hey, like I did it this way, but I also know that in ES6, there's a method on strings called greatest letter that we can use. So they'll be like doubly impressed because they know you can do it in a more like low level manner, and they also know that you're aware of the API. So it shows that you're actually knowledgeable about the language. So I think in your case, like with Python, Python's extremely like robust, right? So I would mention exactly what you just said. Like, oh, hey, I know there's a lot of string constants that exist. Do you want for me to do it this way? I can use X, Y, Z, or I can just show you how to do it in a more lower level way. Because now they know, okay, Menage is not able to show me how to do it in the low level way, but they also know how to use Python as a language. They're familiar with the API. So I think that shows like expertise. Just my take on things. But very happy with this question. I really enjoyed this question. I'll definitely be adding it to my list once we're done here. Let's get to another one. So yeah, we've already done 4. Like nowadays, if we do like 5 questions, I'm really happy about that. I'm very curious to see how it's going to be once we start getting to mediums. I suspect that like 2 or 3 will become the goal for any given stream. All right, a potentially high quality question that we have here. Let's check it out. A sequence of numbers is called an arithmetic progression if the difference between any 2 consecutive elements is the same. Given an array of numbers R, return true if the array can be arranged to form an arithmetic progression. But is this, do they really not want us to do? So we just need to check the distance of every single letter in the string, or every single value in the array. Now, the easiest thing that comes to mind is sorting it, but no, actually we don't need to sort it, because whether it's sorted or not, the distance should always be the same, right? So I think there's something that we can do here that's really cool. Yeah, I think we can do something here. So first, let's check our bounds. So we're always going to have at least 2 things, right? So we can say, let's get the original distance. So we do math.abs of array at 1 minus array of 0, right? That's going to give us the distance that now everything has to go from. I think what I can do, I'm going to use a JavaScript function here called every. And here we get the element, the index, and the array. And what can I pass? Index and the array. Is there a way that I can start at a different index? Element in this arg, this truly range of elements is set before the first invocation. Change their value. All right, mutate the array of for all this value. Testing size, checking if 1, using arrow functions. Okay, I don't think we can modify the index, but that's fine. Let's do this. I'm going all over the place. Okay, so what I want to do, we can return array.every, which we do what do we get in every? We get element, index, and array. Every num, index, and the original array. I'll just put orig for original. Here what we can say is if index equals 0, we just return true. Else, whenever it's 1, we just return can we just do math.abs? Yeah, return math.abs of orig at index minus orig at index minus 1 is equal to distance. Will this work? Okay. If index is 0, return true, else return orig at 1 minus orig of index minus 1 equals index. Every num. Can we just say num minus math.abs of, so this will be like 5 minus the previous one is equal to the same distance. Really? Distance here should be 2. If index is 0, we return true. Then we get to index 1. So I say 5 minus, let me see, org of index minus 1, 3, 5 minus 3 is 2. That equals to index. Oh, okay. Wait, it wants us to see if we can reorder it. 1, 3, 5. Okay, 1, 2, 4. Okay. Yeah, we need to, I think sorting it, I mean, I don't know if that's the fastest way, but I know sort A, B, A minus B. Let's just go for it, right? For let I equals 1, I less than sorted dot length, I plus plus. Let's do const distance equals math.abs, or it's already sorted, so we can just do array of 1 minus array of 0. If array of I minus array of I minus 1 is not equal to distance, then we can return false, else return true. Let's see this one. 1, 3, 5. Okay, maybe we're going too fast here. This should be 1, 3, and 5, right, for sorted. And of course, we're not using sorted here. That's definitely going to cause this to fail. Let's run this again. True and true. True and false, true and false. False and true. Okay, that's going to be interesting. So that just completely changed everything here. I mean, if we had a lot of elements that were to rearrange them to form an arithmetic progression, I once again made the same mistake. Let's submit this now. There you go. Okay, we got that piece. Great questions. I like the tree ones. I have to go. Awesome. Hey, yeah, no problem. We're about to wrap up. This is actually the hour mark already, so that's a perfect time. Well, Manoj, thanks so much for joining. Really appreciate having you here as always. And yeah, hope to see you again tomorrow. We'll definitely be around doing more questions. Hopefully this helped. I'll just keep talking to myself for a little bit. Cool. So yeah, 48.73. I'm going to run this one again. 89.82, but I'm curious to see what discussion says. O of n and O of 1 space. Okay, so I don't even want to look in there. What's our bounds? 1000. If I sorted it, O of 1, O of 1, O of n and O of 1 space. Oh, I think I see what we can do here. Should always be the same distance to the next one that's filled in, right? So if we have, right, like if we have 0, 1, 2, 3, 4, 5, if I put 1 here, put 1 here and I put 1 here, there should always be the same distance. And that distance will be governed by the distance from the first one. Well, if it's 500, 502. So go to the first one, get the distance. Yeah, I think that's what we can do. I can keep count like that. Now, what do I know if I have it? Is this an arithmetic? It's the same. Difference between any two consecutive elements is the same. Okay, I think I know what we can do here. Something else we're going to try. We're going to create, let's say, const counts is new array of 1001. We're going to fill this up with 0. Then we're going to go for let I equals 0, I less than r dot length, I plus plus. We're going to do counts at r of I plus or equals 1. So I'll have a 1 at the 1, we'll have a 1 at the 3, we'll have a 1 at the 5. Now are these 1, 2, 4, are these all unique? Well, I guess if it's not equal to 0, find the first, so let's do find index of first non-zero element. So find the index of first non-zero element. Then we get the distance from this one to the next one, and those should always be the same. What would be a nice way for me to calculate that? I mean, I guess I can just get the distance the first time. Find index of the first non-zero element. From there, find index of second non-zero. Get distance. Same loop as above. So we want to find the index of the first non-zero element. So first non-zero equals counts that find index val not equal to 0. Okay. Let's see, find index MDN. Okay, can I give it a starting index? Callback function, value of the element. Oh, how about index of? Does that let me pass in from index? Beautiful. I'm gonna use that. I like that one better. Let's do counts.index of. Oh, but index of. That's unfortunate. Okay, first non-zero. Now we can say for. Let's do let first non-zero. We can say first non-zero less than, let's see, counts.length. First non-zero plus plus. If counts of first non-zero is not equal to 0. Let's create another one. This is second non-zero. We can make second non-zero equals first non-zero. Or actually, we can just get the distance as soon as that happens, right? We have, maybe I don't even want to set. What I should do here is say let I equals first non-zero. I promise I'll explain all this to you in a little bit. We do I here. If counts of I is not equal to 0, then let's do let distance equals 0. We can say distance equals I minus first non-zero. And now the distance always needs to be the same. But I should probably take distance equals counts of I minus counts at first non-zero. Okay, that will give me the distance if counts of I not equal to 0. But now we want to find the same thing. Seems kind of a distance. Let's second non-zero. Maybe here I say second non-zero equals I. And then we finally finish off doing a very similar loop from here. Just comment all this stuff out. Oh, wait, what happened here? Okay. For let I equals second non-zero, I less than counts dot length. Now we can always do, now we just have to, for every non-zero, we calculate the distance with the previous one that we found. And then we update. Yeah, this seems like way, not like in love with this, but hey, if counts of I not equal to 0, if counts of I minus counts of second non-zero not equal to distance, we return false. Else, what do we do here? We say counts of I minus, okay, here we can do second non-zero is I, and then at the end we return true. Crazy code. True, 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 false. Okay, yeah, there was bound to be an issue here because this is a lot of stuff we're writing. Let's go through this. Counts of I, counts equals new array, I equals 0, I less than r dot length. All right, counts of ri plus or equals 1. Find the first index of the first non-zero element, right? Because that's where we're going to start. Counts dot find index of val, where val is not equal to 0. And counts is going to give me something here, second non-zero and then distance. Now starting from the place that we just found the first one, I less than counts dot length, if counts of I, oh, this should be plus 1, right? Because we want to start from the next one. If it's not equal to 0, then we say the distance is equal to this counts of I, whatever number that is in counts. Should it be counts of I? Because counts of I is just going to be some number like 1, 2, 3. It should be I minus counts of first non-zero. And this should also be first non-zero. Second non-zero equals I. Starting now from I, second non-zero to I, if counts of I is not equal to, if I minus second non-zero is not equal to distance, return false. Let's run this. True, 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 false. I think I'm making some dumb mistakes here, but really what I'm trying to do is I'm trying to do the same thing, but now just with a single static array. So this would make it linear time with constant space, right? Which is better than what we had earlier, which is our n log n. But there's probably a better way of doing this. We just need to make sure, like, for every non-zero element, the distance is the same to the next non-zero element. Or I guess we can always keep track of the count. Yeah. I might, maybe we can leave this for like a weekly roundup, because since we're over the hour mark now, I want to keep these to like an hour just to make them consistent for viewers. So with that being said, make sure you check my website. So now I just made it raphaelslist.com just to make it a little bit easier. I'll be sure to upload all these new questions to the website so you can go and find, you know, the different streams and the topics, anything that you want to learn about the question. Make sure you subscribe to the channel. It really helps me out a lot. It allows for me to extend my reach and get this out to more people looking to start their own LeetCode journey. And let's see, anything else? I guess we can leave off with something kind of funny. I historically used to pay someone to cut my lawn just because I didn't really want to do it myself. But today I invested in an electric lawnmower. I got it used on OfferUp, and I tried a little bit of it out already, and it's been awesome. So I'm just looking to. I'm probably gonna go back to it now to keep checking it out because it's pretty cool. Feels pretty cool. So with that being said, happy coding, and yeah, we'll see you all tomorrow for more LeetCode. Oh my God, I can't talk right now. We'll see you all tomorrow for more LeetCode. Happy coding all.